So the last speaker of the morning session is Professor Boris Pioline from CNRS and Sorbonne University. He has been done a lot of works in relating supersymmetric series and supergravity. And today he will tell us about modularity of Donaldson-Thomas invariants on Calabi-Yau threefolds.
Thank you very much. So it's a great pleasure and honor to speak at this wonderful meeting. Thanks a lot to the organizers for inviting me and to all of you to come to my talk, whereas there are so many exciting talks taking place in parallel. So my talk will be based on the two papers, one of which appeared about a little bit more than a year ago with Sergey Alexandrov, who is here, Soheyla Feyzbakhsh, a brilliant mathematician from Imperial College, Albrecht Klemm, that you all know, and Thorsten Schimmanek, who's a postdoc, was with us in Paris and now is in Utrecht. And there is some follow-up with Charles Doran in Edmonton, which hopefully will appear in a few days from now. And I should just point out that Sergey will also speak on a related topic tomorrow morning, although from a rather distant perspective. So my talk will be fairly mathematical, but the motivation comes from physics. We just spend a few words on this. As Ed Witten beautifully explained in his lecture, black holes carry macroscopic and large entropy proportional to their horizon size. And an open question for any putative theory of quantum gravity is to give a microscopic understanding of this entropy from some large number e to the s of microstates having the same macroscopic characteristics. So famously, string theory has achieved this goal already a while ago, starting with the work of Gopakumar-Vafa more than 30 years ago. I should also say many important contributions from Ashok Sen, and many other works in between since then. So string theory does provide a quantitative description of the black hole entropy in the context of BPS black holes in vacua with extended supersymmetry. BPS means that the black holes preserve some fraction of supersymmetry. And at least at weak coupling, we can understand those microstates as arising from so-called D-branes, wrapping cycles of the internal manifold, coming from 10 dimensions down to 4. And in many cases, we can count these states accurately, and in this way obtain confirmation of this prediction coming from gravity. So it confirms the consistency of string theory as a theory of quantum gravity, but it has also opened up many fruitful connections with mathematics. And this is really the main motivation from my point of view, at least for pursuing even now, 50 years after, this research direction. Now, a lot of this has been done in vacua with extended supersymmetry, but the context I want to focus on is as reduced supersymmetry, as small as it allows to define BPS states, namely type 2 strings compactified on the compact Calabi-Yau threefold, in which case there is a very precise mathematical description of this object that we're trying to count. Namely, they are stable objects in the so-called derived category of current sheaves associated with this space X. So this is some souped-up version of the set of holomorphic vector bundles on this internal manifold. Every such object carries a charge which is given by the Chen character. And this is, from the physics point of view, the electromagnetic charge. We think of it in terms of the D6 brane charge, which is the rank, the D4 brane charge, which is the first Chen class, D2 is Chen 2, and the D0 brane charge finally is Chen 3. Now this becomes, therefore, a very precise question in Donaldson-Thomas theory, which is the proper setup to count those states. For fixed Chen vector, can we compute the number of such states, or mathematically the generalized Donaldson-Thomas invariant, counting semi-stable objects of fixed class gamma for fixed values of the shape of this internal Calabi-Yau, which in the mathematical framework involves a choice of Bridgeland stability condition. Now, I should emphasize that Bridgeland stability conditions are much much more general than just the stability conditions which come from string theory. And in fact, this problem can be asked away from the physical slice corresponding to string theory. And it gives us very powerful techniques to compute quantities of eventually relevant for physics. Now, if we can compute these numbers, in principle, we want to analyze their growth as the chain vector is scaled up and see if it matches the expectation from gravity. And this is, of course, in general, very hard. Even computing those numbers is very hard, except for very specific charges. But if we have some further structure, namely modular properties of certain generating series of DT invariants, then we can use this modular behavior to predict the growth and see if it matches with gravity. Now, in general, there's no statement of modularity for any such DT invariants. But as I will explain, there is a prediction from physics that certain generating series of so-called rank 0 DT invariants, so those are those for which chain 0 is equal to 0, do have specific modular properties. And that's what it's a physics prediction that we want to test it and see if it's true. And if it is true, then we want to exploit it to extract more properties of these invariants. Okay. So today I will explain how to combine knowledge of standard enumerative invariants in symplectic geometry, namely Gromov-Witten invariants, which just count terms in X, and wall-crossing arguments in this space of Bridge stability conditions to compute rigorously many of such rank 0 DT invariants, and then provide checks of this modularity to high precision. I've put here in parentheses mock modularity. In fact, there are some modular anomalies for certain class of charges. And in fact, it will be the topic of Sergey's talk. In this talk, I will consider cases where this issue does not. So hitting the wrong button. But so conversely, once we trust that these generating series do have modular properties, then we can in fact compute an infinite number of them. This is slightly worrying. I can do much about this. Oh, I know what's going on. Perhaps is this. Yeah, let me just put it back. Yeah, I'm there actually. Okay. All right. So conversely, if we postulate these modularity properties, we get access to an infinite number of such DT invariants. And we can use these predictions back in the algorithm to get new constraints on Gromov-Witten invariants. And in particular, be able to evaluate them to higher genus than was possible before that. So in this talk, I will restrict to two cases where this mock modularity does not arise, just ordinary modularity, namely one parameter hypergeometric models with one unit of default brane charge. So this class of models includes the quintic, as well as many other examples with one Keller modulus. But the restriction to one unit of default brane charge allows us to avoid this mock modularity issue. Now, I wonder if this is due to my computer or maybe I'm hitting a button which escapes. Okay, so the first part of the talk will be about this one parameter hypergeometric models. This is the paper that appeared already more than a year ago. And then hopefully in the last part of the talk, I'll discuss the class of two parameter models, not of the modular types, but those which have K3 fibrations that are interesting for various point of views. But in particular, there is also another notion of modularity in those models, and one can hope to play these two notions together to get further mileage. Okay, so I will start first of all by reminding you of some properties of this enumerative invariants in compact Calabi-Yau 3, how they are related to each other, and how we can exploit them to compute these rank 0 DT invariants. Okay, so let me start with the Gromov-Witten invariants. They are very well known. So n beta g counts genus G curves inside with fixed class in homology class in X, and fixed genus G are really embeddings of sigma of genus G curve into the target space. And they depend only on the symplectic structure of the Calabi-Yau, not the complex structure moduli, and they take rational values. And physically, they arise, first arose already many years ago when we tried to understand the low energy effective action of string theory compactified in such Calabi-Yau. There are certain couplings which involve the square of the Riemann tensor and some graviphoton field strength, and the dependence on the Kähler moduli is encoding on some function fg of t, which is determined by this Gromov-Witten invariance. In fact, this comes physically from worksheet instanton contribution to this complex. Now, those are actually computable up to a certain genus. The genus 0 and genus 1 joining series can be computed using Eurosymmetry. This was the breakthrough of Candelas et al. Many years ago. And to higher genus, we can also get access to them using so-called holomorphic anomaly equations developed by BCOV, which allow to compute them recursively as the genus is increased. However, you do need to specify certain boundary conditions to solve those equations near the discriminant locus or mem points in order to fix the ambiguities in these equations. And this puts a practical bound on the maximal genus that you can raise, and then you can access using this method. For the quintic threefold, in particular, one can see that we run out of such constraints when the genus is equal to 53. This is a number which was obtained already in 46 by these authors as a theoretical upper bound, but has only been reached very recently using improvement of this direct integration method. Okay, but those numbers are rational numbers that you can't really think of them as counting some BPS states. And already a long time ago, Gopakumar-Vafa understood how to convert those rational numbers into actual integers, the so-called Gopakumar-Vafa invariants. They also depend on beta and the genus G via this rather complicated multi-cover formula. If you extract the genus 0 part of this series on both sides, you will recognize the usual relation between genus 0 Gromov-Witten and this integer invariance at genus 0, sum over 1 over divisor Q. But in general, it's rather more complicated. And another property of this, so those numbers, however, were conjectured to be integer. And this has now been proven mathematically by Yonel and Parker, who also established that if the genus is large enough for fixed beta, then these numbers, these GB invariants vanish. This is the so-called Castelnuovo bound. They did not get any explicit form for this maximal genus. And in fact, one of the outcomes of our analysis will be a mathematical proof of the Castelnuovo bound in this context, subject to some assumptions which I will mention. Okay, so those are the Gopakumar-Vafa invariants. And physically, what the genus 0 ones count BPS bound states of D2 branes with some charge beta, arbitrary D0 brane charge, doesn't depend on D0 brane charge. But the interpretation of the higher genus GB invariants is more subtle. In fact, they provide a refined counting of these states, keeping track of their angular momentum, as I'll explain in a second more. And the way this formula arises is from some kind of one loop Schwinger computation with all those BPS states running in the loop. That's how these authors arrived at this rather Baroque formula. Now, more precisely, the way to understand those numbers is to think of type 2 strings as M3 compactified on a circle. These D2 branes wrap to M2 branes wrapping a curve inside X. And now what they produce, if the circle is very large, are BPS black holes in 5 dimensions. And those states carry 2 angular momenta, J left, J right, because the little group is SO4 rather than SO3. And the precise relation is that if you keep track only of the left angular momentum or the projection along some axis, then the number of microstates of such fixed D2 N2 branch charge and angular momentum is the linear combinations of these GB invariants involving binomial coefficients. Now, there is also a prediction from black hole entropy that those numbers should grow exponentially fast as you increase both beta and m, keeping this particular ratio fixed. Namely, they should grow in this way. And there is numerical evidence that they do in this way. But as far as I know, there is no mathematical strategy to establish that property. And it's so it's an open problem, I think, which is interesting for mathematicians. Physical understanding. Well, we do have a mathematical understanding, and I'm not sure I can convert it easily into physics intuition. And well, here I think, no, okay, rather maybe I should say better that this is the external bound for black hole in this way. But how to determine that particular bound is yeah, I don't have a direct physical way of getting an exact function Gmax of beta, which will appear later. Whether we can we have a physical guess for Gmax of beta. Well, I will be mostly interested in one parameter models. There is, of course, a conjecture for what is this function for the quintic that's been there for a long time, but I want to prove it and generalize it to other models. Okay? Okay. Yeah, this is numerical analysis, basically using this GB invariance up to genus 50. Also, you get the beautiful fit. I did not put the plot here, but you can do it. Most authors did it with less data already in 2007, and you can confirm that this is true. Yeah, of course, of course. This is the leading behavior, and we cannot even understand mathematically the leading behavior. So what people have been able to do is to compute the first one over beta correction. I don't think they were able to match the log. It's an interesting question. We might already start to have the numerical data to address this question. Okay, at any rate, my focus is not on 5D black holes, but on four-dimensional black holes. And one way to do this is to consider, rather than M theory on X times the circle, let's put M theory on a so-called Taubenet space times R. R is the radial direction. This Taubenet space is asymptotic to S1 times R3. So from infinity, it looks like a circle compactification, but it has this cat with flat space in the middle. And physically, you can understand that this descends to a so-called D6 brane wrapping the full Calabi-Yau. So this is already closer to four-dimensional BPS state and general one. And so there's also a precise mathematical definition of such counting. In this case, so if the D6 branch charge is equal to 1, and it doesn't really matter what is the D4 branch charge, we can put it to 0, then mathematically, those are, as understood by Panaripande and Thomas, those are described by so-called stable pairs. So F is a pure one-dimensional sheaf. It means it's supported on a curve with a certain Euler number, which is the D0 branch charge. I don't really want to explain more about it, but there is a well-defined moduli space associated to it. And you can define this so-called PT invariant as the Euler characteristic of that moduli space. And it's a very well-behaved mathematical construct. And because this, what we only changed was the geometry near the origin, only this is flat, one expects the same type of relation between the low energy effective action in flat space as in on this space. Sorry again? Well, it's yeah, of course, richly flat, but it looks like R4 in the vicinity of the tip. That's what I meant. So this led to this expectation or derivation, physics derivation by Vafa and Linde of this relation between the generating series of PT invariants and the same topological amplitude which arose previously. And a mathematically precise version of this relation was obtained by MNOP and takes this form. So this generating series of D6 brane indices with 1 unit of D6 turns out to be given by this infinite product formula where the data from this D2, D0 brane comes in this GV invariance here. So this formula was conjectured, but then proven for a large class of Calabi-Yau threefolds. And you can think of it as being a formula that holds order by order in powers of Q on both sides and e to the by t beta on both sides. So you can translate any information about PT into information about GV, vice versa. In particular, this Castelnuovo bound, which I mentioned before, is now a lower bound on the zero-brane charge for PT variance. And if you try to work out this relation or close to the bound, you can easily see that the leading terms will be linear. So there'll be a linear relation between PT and GV of that type. But then there will be some nonlinear corrections and evolving as you further expand this product. And you'll notice that the leading term looks somewhat similar to the 5D black hole degeneracies, except for some shift of the genus. But importantly, there are these terms here which do change, in fact, the asymptotic draw. And again, it's an open problem to determine directly the asymptotic growth of such PT invariants. Now, originally, we want to count these deep brane bound states with arbitrary charge, and let me run quickly over the mathematical formalism in which this is done. So as I said, we have to look for stable objects in the so-called bounded Dirac category of curved sheaves. So what that means is that the objects are some complexes which have only a finite number of slots of sheaves with the maps from one to the other. The actual charge of an object is the alternate sum of the strength characters of each of the terms in the complex. And so in this category, we can define a notion of stable objects. But for this, we need to introduce further information, namely the so-called Bridgeland stability condition. So Bridgeland stability condition has two parts. One, which is very clear from physics, is the so-called central charge. So this is a linear map from the charge lattice to the complex numbers, whose absolute value gives the mass of the state. But then there is a more elusive component, A. A is the so-called heart of the structure, and it's an abelian category which determines a subcategory of C, which determines the possible constituents in which a state can decay. And I will spare you the details of the axioms for this heart. But one important point is that for any object in the heart, then the imaginary part of the central charge has to be bigger than 0. And if it is 0, then the real part has to be negative. And then there are several other axioms. Now, if this space is non-empty, then Bridgeland has shown that it's a complex manifold whose dimension is the dimension of the quadratic group of C, which is in fact just the dimension of the lattice of charges. So on the Calabi-Yau, it would be B0 plus B2 plus B4 plus B6, if you or this formula, just by indicating the value of the central charge on any basis of the lattice. But the main question here is whether it exists or not. Physically, of course, we expect that it should exist, but it's only for very few examples that mathematicians were able to actually construct the stability conditions. This includes this quintic threefold and a handful of others, but in general, we don't know. Although there is a clear strategy to do this, which will be in fact be important later. But right now, let me just say that this DT invariant, so I'll denote it by omega bar of sigma and gamma, is again some weighted order number of the moduli space of semi-stable objects, where the notion of semi-stability here involves looking at the phase of the central charge for all sub-objects and requiring that it should be less than the top. By the way, I should point out that Tristan Collins gave a very nice talk yesterday, also using visions and elliptic conditions. And might want to look up his slides if you're interested in this topic. So these numbers here are not in general integer, they are rational, but there is a conjecture that, again, through some multicolor formula, they will become integer. So instead of having 1 over k cubed, like in Gromov-Witten theory, it's 1 over k squared. This conjecture is actually a theorem in the context of quiver representations, but in this particular context, it's a conjecture. But of course, for physics, it's an important, it's obvious, and it's necessary for being able to identify this counting of physical states with this particular invariant. Now, the key fact about this, of course, is that it depends not only on the Chern vector, but also on the stability condition. And because it's integer, it can only jump in some real codimension 1 walls. And it's the dynamics of these jumps is very well understood both magnetically and physically. There is a universal wall crossing formula that allows you to compute the indices on one side of the wall from the knowledge of the indices on the other side, except that it's very hard to determine even the location of the potential walls, which are actually populated. In general, it will be some dense set of walls in Keller modularized space. Okay, now, so the invariants that I talked about before, the GV invariant at zero, at genus 0, as well as the PT invariant, are actually special instances of this general theory where you take the Chern vector to be 0, 0, beta n, or 1, 0, beta n, with some signs which I'm not being careful here for convenience. Now, as I alluded to before, the main interest will be on rank 0 DT invariants, counting D4 branes, because that's where we expect modularity properties. So this omega of 0, p beta n. P is a class in H4, so you can think of it as specifying a class of divisors, 4 cycles inside the Calabi-Yau. And then beta and n are again the D2 and D0 brane charge. Now, why do we expect modularity? There is a very simple argument which is been known for many years, going back to Malles and Astromenger written in this context, namely the fact that these D4 branes wrapped on the 4 cycle, they are really coming from this N5 brane wrapped on the divisor times the circle. As you reduce this 5 brane on the divisor, you get some 2-dimensional CFT, or rather superconformal CFT. And therefore, this CFT on the torus on the elliptic curve would have modular properties. So specifically, this DT invariance can be argued to be equal to certain Fourier coefficients in the elliptic genus of the CFT. So elliptic genus is something like this trace in the Hilbert space of the CFT. It has a theta series decompositions because the dependence on this D2 brane charges is actually determined by some spectral flow symmetry. So if you extract from this theta series decomposition the coefficients, they are themselves functions of Q. The Q bar dependence disappears because of this insertion of the sign here. So it's an index. Then the expectation, well, the claim is that first of all, these Fourier coefficients are equal to these rank 0 D4 invariants. And furthermore, so I'm skipping some details. Of course, I don't want to get into the details of this formula. Just to mention that this lattice, this is a theta series for a certain lattice, which is H4 equipped with a quadratic form coming from the cubic form on the cubic form on the Calabi-Yau. So at any rate, because from the CFT, we expect that this elliptic genus should be a Jacobi form, and therefore the Fourier coefficients should be vector valued modular forms. But before that, we can actually even predict the growth of these Fourier coefficients just by computing the central charges of the CFT. This was at least when the divisor is very ample, those are simply given by the Euler number of the divisor or the holomorphic Euler number or the left and right moving central charge. And using the Cardis formula that Sergey Alexandrov was talking about in the first talk, you get precise match with this Eckenstein-Hawking formula. But so this is about the growth, and essentially this growth comes from exploiting the modular property, which is a consequence of the CFT symmetry. So at the level of the generating series, the statement is that they should be vector valued weakly holomorphic modular form of a certain weight. So the vector valued part comes from the fact that this mu A, I was too quick here probably. In this, sorry, this is the wrong side. In this theta series decomposition, there is a finite number of terms in this sum, which is labeled by cosets of mu in lambda mod lambda star. That's what you get. That's why you get a vector. Okay, so this is a physics prediction, assuming that this divisor is very ample. Basically, you have a single fibrane wrapping the divisor. And in general, we expect something worse. Namely, we expect modular property, but this will be the subject of Sergey's talk. I'm not going to talk about it here. Now, let me just say a couple of words of what should be the mathematical origin of these modular properties. Well, it's likely that similar to the work of Nakajima on instantons in LA spaces, it should come from the action of some VOA on this cohomology on the space of stable sheaves, but no one knows how to make that precise yet. There is one instance where modularity is clear and established mathematically, which is when this Calabi-Yau is K3 fibered. And if you restrict attention to 4 branes that wrap the K3 fiber, that's fibrations, that are so-called vertical D4 branes. Now, these authors, going about less than 10 years ago, explained that you could actually relate this vertical D4, D2, D0 indices to the so-called Notor-Lefschetz invariants of the fibrations. I will get to that in the second part of the talk. And in that case, there are mathematical results that guarantee that it should be. But in fact, in that case, there also no modularity. So that's why we'll consider this. Okay, so this was basically the review of the background, the techniques that we want to use to compute this. Now we want to test actually this prediction for some specific non-compact Calabi-Yaus. We can't take the most any Calabi-Yau. So for these Walkersing arguments, we need to have a small space of parameters. So what we'll do is we consider pk rank 1 Calabi-Yau threefolds, so 1 Keller parameter, and compute the first few coefficients in this Q expansion and try to see if they indeed match the coefficients of some vector model. This is not the first time, the first attempt in this game. Already Gayotto, Strominger, Yin tried to do this for the quintic and some other hypergeometric models. But at the time, there was poor understanding of those Walkersing constraints. And in fact, there was no mathematical way of computing these coefficients. So they had to resort to some guesswork. And what we'll see, in fact, is that their guess was right in some cases, but at least they will confirm the guesses and give overwhelming evidence for this modularity. So we'll compute these terms rigorously using results by Soheyla Feyzbakhsh and Richard Thomas, which have developed general relations between rank R DT invariants and rank 0 and rank 1. So rank 1 DT invariants are closely related to PT invariants and therefore to GV invariants. So if you like, this is the topological string side of the correspondence, whereas this relates them to any rank, in particular rank 0, which is what we're aiming to compute. But in principle, it also holds for higher rank. Now, I will explain the key idea, not the details, but the key idea that goes into these relations. And the idea is to use Walkersing in a family of Bridge stability conditions which are not physical, and in fact, they are not even stability conditions in a strict sense. They don't satisfy all of the axioms, but enough of them that this Walkersing formula is still applies. So it's basically considering some degenerate central charge, which looks like the large volume central charge. So in the footnote here, I've recalled you what would be the central charge at large volume. Would be the integral of the Chern vector times e to the Keller form. So B and T here are the real and imaginary part of the complex scalar modulus, and H is the generator of H2 of XL. So if you expand this in if you expand exponential and integrate over, you will get some kind of cubic polynomial in T. But the one that we want to use for this argument is some kind of degenerate version where we set to 0 the coefficient of CH2. That's what mathematicians found convenient as a first step to construct bridge stability functions. So maybe I should show the next line here. So this is in fact the first step in constructing genuine stability conditions near a large volume by first trying to construct a heart for this one, and then perform so-called tilting to obtain a bona fide stability condition. Now, without going, and so for this one in particular, there is a natural choice of part, which I don't really want to go into, but it exists for any Calabi-Yau. We don't need to assume that it's the quintic line. So that step is general, and the wall crossing formula holds. Now, the good thing about it is that wall crossing is much simpler in this unphysical slice than in the real one. In particular, in this B field and kind of volume direction, upper half plane, just nested half circles. And more than that, there is a notion of empty chamber. So conjecturally, there exists an empty chamber. So whenever the Chern classes violate this inequality, then the index will be 0. So this inequality is, as you can see, is quadratic in the Chern classes. So Ci here is the integral of Chi times the hyperplane class to the right power. So in order for a stable object to exist, this quantity has to be 0. If it's so you see this is some kind of half circle in dotted line in this graph plane. So if you are down here, this is violated, and so the index here is 0. And if you have enough control on the walls that separate you from here to infinity, then you can actually compute the result at large volume where you are interested in it. So this inequality is a conjecture, but if mathematicians have been able to prove it for the quintic and a few other examples, and if it's true, then you can go on to the next step and construct the Bayesian stability condition. But so everything I'm going to say would be subject to the validity of this inequality. Now, by studying wall crossing between this empty chamber, if it exists, and the large volume, then Feyzbakhsh and Thomas were able to give some general relations between these D4, D2 indices and PT invariants, which are themselves related to a GV. Now, I'm going to explain the formula just to state it. So I should say that in those series of papers, they gave some general relations, but not explicit enough to actually get the number out of it. And so we had to work hard with the Soheyla to make a statement which was actually concrete and predicted. So the statement goes as follows. And just to preview, it will involve studying wall crossing of some anti-D6 brane from an empty chamber to large volume, where it's related to PT. And it will pick up some bound states with D4 branes, and those are the contributions that we want to compute. So let's take a smooth Calabi-Yau threefold with the one modulus. So PK is, assume that the PK group is just Z, and assume that this BMT inequality is satisfied. And so we fix beta and M, the D2 and D0 brane charge, and we want to compute this inductively. So there will be some conditions on beta and M for which we can do this. Part of the condition is that there should exist an empty chain. And to state the condition, sorry, this is more technical and more than you ever want to know, just define this ratio X, which is the D2 brane charge normalized by this is the self-intersection of the Calabi-Yau. And alpha is the D0 brane normalized to D2 brane. So there is some plane alpha and X here. And there is some function f of x, which is shown in blue in that space. And the claim is that whenever alpha x lies above this blue curve, then we can actually compute PT recursively by the formula on the next slide. So the formula says that whenever alpha is bigger than f of x, then PT of beta m is equal to a sum of PT of beta prime m prime times some rank 0 DT invariant with 1 unit of D4 branch charge and some D2 and D0 branch charges, which are of course constrained by charge quantization. So what's important is that the formula is recursive. So the beta prime m prime, which appear on the right-hand side, they are always less than beta. And the same, well, yeah, and yeah, so that in that sense, it's recursive. Now, a direct corollary of this theorem, so which involves the wall crossing for an anti-D6 branch. So the charge here is -1. The corollary of this, you can derive this Castelnuovo bound on PT invariants, namely a lower bound on M as a function of beta. So this gives you minus G max of beta, which in fact, for the quintic, this formula was conjectured already by Klemm and others, but now this is a mathematically rigorous statement, assuming that the BMT inequality is satisfied. So already we got this, but now what we are really interested in is computing these omegas. And so what information do we have? Well, we know how to compute this GV invariance using this direct integration method up to fairly high genus. So we can convert this from using MNOP into values for this PT beta n. And so we can just exploit this formula to extract omega by choosing astutely the beta and m that you start with. Anyway, this is probably more than you want to know. Let me just go to the result. So using this, we can compute a large number of coefficients in this Q series, not only for the quintic, but for a family of so-called hypergeometric threefolds. I think I have the family here, right? So there are 13 of them, including the degree 6, degree 8, degree 10, some more exotic examples. In this column, you see this is the self-intersection H cubed. Here you see the number of so-called polar coefficients. So there are the terms with negative powers in the Q series, from which the whole Q series will be determined if you assume modularity. So for the quintic, you have to compute 7 coefficients. And in some cases, actually, there are some conditions on the coefficients themselves for the existence of the modular series. But okay, most cases, they're not. Okay, so what we find is that in all cases where we could carry out this program, we can match this Q series to a basis of vector valued modular form constructed in a very simple way using some theta series associated to the lattice, as well as some Eisenstein series, Dedekind function, holomorphic set derivatives. This is actually an overcomplete series, but you can use this to try and find, and you do find in all examples such a solution. So let me, just to impress you, show all the coefficients that we could compute for using knowledge of GV invariance up to genus 53. We could compute more than 20 terms in this vector valued German series for the quintic. So the coefficients which are underlined are the so-called polar terms, those which have total negative power. So just knowing these 7 numbers, you can predict everything else. But we can also compute the other ones independently, and we find matching on those. So that's a striking consequence of, so here's the particular combination that provides this. And in fact, it is the one that Gayotto, Strominger, and Yin were able to guess. Congrats to them. But now it's a derivation. But you can also use this the other way around. So now that we assume that this is true, we get an infinite series of such coefficients. So we can feed it back into this algorithm and get further knowledge of this GV. And in this case, we could push it up to genus 16. So if you just care about enumerated geometry, maybe you should also care about the black hole counting. Anyway, Gayotto et al. Were not always so lucky. So for extend, they predicted this. There were just two product terms. They predicted this result. In fact, the correct result from these arguments, assuming that this BMT inequality is correct, is differs by one. And so, okay. So I think I have about 15 minutes left before this. So I'm going to switch to the second part of the talk. But maybe it's a good time to take questions. For the modularity. So the physics, basic physics reason is clear from this picture of wrapping the fibrine on the divisor, right? So you have the elliptic genus, which would be modular. Now, that's good enough for in this case. But if you have this, if the divisor is not ample, then there are, or if you have more than a single fibrine, you don't have enough control on the fibrine theory to know what the result should be. And I think Sergey will explain another strategy to establish the precise modular, modular properties. But for my purpose, that's all. And it's okay. So this was the story about a year ago. Now we try to extend this to two-parameter models, and so a nice class to look at are two-parameter Calabi-Yau threefolds, which also have a K3 fibration, and not only them, but also their mirror. So in general, it's not true that the mirror of a K3 fibered threefold is also K3 fibered. For simplicity, we're going to make this assumption. Now, an interesting part is that there will be also some associated modularity associated with the fiber, and also this connection to Notoriously invariants. So the aim will be to compute this Notoriously invariants and check modularity. So now we're back to classical geometry. So on the A model side, this X, which has so pk rank 2, will be fibered by pk rank 1 K3 surfaces, fibered over some P1. And each of the fiber will, in order to have pk rank 1, will be polarized by a degree 2m line bundle L. So m is an integer to pick. And on the mirror side, y will be fibered by pk rank 20 minus 1, which is 19. Polarized, so in fact, by the mirror of the K3. So this is one case in which mirror symmetry of the Calabi-Yau 3 comes from mirror symmetry of the K3 fiber. So on the B model side, the pk rank is 19, and there is a polarization by this lattice E8 plus E8. U is the hyperbolic lattice, and this is just the one-dimensional lattice with norm -2. So these fibers, this is an old story, which is actually important in physics at the time of heterotic type 2 duality, that these fibers here are related by mirror symmetry. Okay. Now, the nice thing about this is that this space, so the moduli space of this polarized K3s, well, of course, is like dimension 1, but it's actually a modular curve for the Ecke congruence group gamma 0m with the Fricker extension. So it means that all the periods can be expressed in terms of modular forms of this. And this, the first example of that was actually noticed by Lian and Yao back in '95, which is to look at the fundamental period of this mirror K3. It satisfies some Picard-Fuchs equation. You can compute it order by order in the parameter lambda. And what they noticed is that if you express lambda in terms of the up module of tau for the given group, then what you get is in fact just a weight 2 modular form. I write it as E2 n of tau. Now I should give a few more information about this modular curve. So it always has genus 0. That's why there exists a module, but it has a bunch of singular points. It always has a cusp, one cusp, a number of so-called Z2 orbifold points, and then an additional singularity, which can be a cusp or an orbifold singularity. Those are the values of the J invariants for the Z2 orbifold points. This is the corresponding value in the tau plane. Okay. Now, so this is about the fiber. We want to fiber this over the P1. So we need basically to determine a map from the P1 into this moduli space of polarized K3s. So it will be covering a branch cover over P1, or a map from P1 to X0 and plus, which is also a P1 with a bunch of. And generally, we can assume that this map is unramified everywhere except at lambda equals 0 and lambda equals infinity. So this is an example of a curve. This is lambda. Lambda is here, and those are the values of the coordinates along the base. And the covering is determined by some kind of ramification profile. So this would be generic ramification, or by some kind of partition of the total degree into a sum of integers corresponding to the leaves of the fibration getting to them. So it's classified by these branch covers. And in fact, the understanding what are the possible ramification profiles was done in this very nice work by Doran a long time ago. And they found out that over lambda equals 0, there are only these possible splittings. So here, for example, the degree can be 2 with the trivial ramification, or it could be 3 as 1 plus 2, or degree 4 as 2 plus 2, etc. So there is a finite list, and importantly, the only possible values of m is bounded, can only take up to 11, and then also n equals to 10 is missing. There's a finite number of such models. In fact, as I argued, there are only 26 such models. I don't ask why 26. But anyway, so yeah, so if in order to have two, so on the B model side, we want to have two complex structure parameters, then the profile over the other point should be of that form, also a partition with two parts, I minus Sj plus S. And there is an explicit formula for how to map the P1 coordinate to this moduli space, to the modular curve. Just take lambda as a product of 1 minus y to the I, 1 minus z2 to the j. You see that lambda equals 0, there will be ramification of order I from this leaf, and order j from the other leaf. Now, I think I'm probably giving too many details here. Just want to highlight that those models are very computable. So if you're interested in the periods of those Calabi-Yau threefolds, so you can basically integrate the K3 period over a particular path on the base. And this is some kind of contour integral of this fundamental period, and just get explicit results in terms of the coefficients which enter, which enter in the fundamental period. So maybe I should have, yeah. So from these coefficients, you can pretty much derive all the periods that you're interested in, at least in the large base limit. These coefficients are very simple for the models with m less than 4. There are some kind of products of binomial coefficients. They are more complicated for higher values. Okay, so well, there is this S parameter. So yeah, so from this you can extract the Picard-Fuchs equation. Yeah, but this is the B model side, and we want also to understand the mirror. So one way to understand the mirror is to extract the Picard-Fuchs equation and apply some kind of Batierev Borisov construction to the corresponding idea. Okay, so but there's a shortcut in some cases. So just from the side of the fundamental, from the knowledge of the fundamental period, you can read off some GLSM construction. So here's the simplest example for Mij equals 1, 1, 1. Then you find some complete intersection of degrees 6, 0, 1 minus S1, J1 in this type of weight. So this gives, but in fact, there is a general way of constructing the mirror, which I cannot go into, in terms of some complete intersection in some Fano fourfold labeled by these indices I and J. Now, this is for any of such model with H12 equals 2. But we want to restrict to those which also have, well, let me say first that from this construction, you can see that as predicted by the Doran-Harder-Thompson general philosophy, this K3 fibration on the B model side is reflected into a Turing degeneration on the mirror side. That's a general fact about fibrations. And so indeed, you can see that there is a point in moduli space where this Xij splits into the product of the union of two Fano threefolds, each of them of rank 1. So you get rank 2 by summing the two parameters. intersecting over an anti-canonical K3 surface of degree m. Okay, but in general, this will not be K3 fiber, just the intersection is K3. And if we want to have K3 on both sides, especially we want K3 vibration on the A model side, because that's where we can make connection to this counting of black holes, then we also need a Turing degeneration on the B model side, and that requires this. All right, so this is, so there is basically a uniform construction of this 26 models, or maybe 49 if you let this parameter S be arbitrary. And you can read off all their, well, the numerical invariants from knowledge of this finite list of Picard rank 1. And in particular, you'll notice that, well, the self-intersection, the cubic self-intersection is such that the fiber has self-intersection 0 as well as intersection to the base. And the Sergonchian class along the fiber is 24. So by Ogiso's criterion, this is the criterion for having a K3 vibration. Okay, so we have this nice family, and I think in just a few more minutes. Some of those examples actually can be obtained in much have been seen earlier in the literature. Some kind of complete intersection constructions. And an important, another fact that I want to highlight is that those are two parameter models, but they admit the conifold transition to one parameter models. And in fact, those ones have transitions to these hypergeometric models that I was discussing before. So part of the hook here is to understand the modularity in one parameter models from modularity in these K3 fiber models by geometric transition. We're not quite there yet, but this is some steps on the way. But in general, they would not be hypergeometric, I should say. Many of those models do not have any toric construction. So it's also an interesting zoo, a small zoo of non-toric Calabi-Yau threefolds, which we don't know how to exercise. Okay, so now very briefly, let's connect to this black hole counting. So the claim is that there is a relation from black hole counting to Noether-Lefschetz invariants. So what are Noether-Lefschetz invariants? Well, if we just think about this moduli space of degree 2m, this happens again. Pressing the combination of two buttons, which is filling the screen. Anyway. So on the A model side, we have these 2m polarized, or these polarized K3 surfaces. They have a moduli space which is 19-dimensional. But it has a very there is a canonical arithmetic cycle in that moduli space, which was constructed. Well, there are several. Well, let me just give the construction. So if you look at the locus where there exists a class in Picard of sigma, so it's both H2 and H11, such that it's square. But if it exists, then you define H to be and mu by these two formulas, and you consider the union of all these divisors, and that's a special locus in this symmetric domain. And so the Noether-Lefschetz number is defined by intersecting this locus with the image of the fiber into this lifting map. And it's actually it's an integer number. It depends both on H and on mu, but it's basically periodic in mu. And so maybe I should, I want it, no, this is too much. So the main claim from the mathematics literature, going to Kudla, Nilsson, and Borchardt, is that the generating series of these divisors, or if you like, the intersection with the sum of all these divisors is arithmetic, and the generating series is in fact a vector valued modular weight of certain weight for a certain line representation. So those numbers are modular from just as a consequence of modularity of moduli space of K3 of polarized K3 surfaces, basically. But what is the connection to to enumerative geometry? Well, first of all, these authors explain the relation, I mean, they conjectured, and part of it was proven, between the vertical GV invariants, so the counting of curves in the fiber with this Notor-Lefschetz invariants, just some simple inner combinations with the factors which come essentially from the Gromov-Witten theory of K3. So knowing NL, you can compute GV or vice versa. Here are the numbers. Yeah, so this is actually a consequence, or you can physically you can think of it as a consequence of heterotic type 2 duality. This series is you can think of it as being the U supersymmetric index. Yeah, and so the relation to the period computation is that the prepotential in the large base limit, S is the modulus of the base and T is the modulus of the fiber. So in a large base limit, the one loop correction to the potential involves some theta lift of this Notor-Lefschetz joining series. You can be very explicit about it. Once you know the GV invariance, you will obtain this potential, or at least the fifth derivative of it, as an inner combination with the polylog, or in this case, just rational function functions. Okay, so I think, yeah, I have to stop here. So basically, using this period computation, you can read off Notor-Lefschetz invariance, and finally check modularity. I don't have time to explain this, but it implies some interesting mock modularity of some analogs of fundamental periods for K3. This is one example where this is all worked out. But so what you find is channeling series which are either vector valued or are meromorphic modular forms with the fast growth. And then using the relation between these D2 D0s, vertical D2 D0s, and D4 vertical D4 branes, we can finally compute this D4 D2 D0 in such way. Okay, so let me just reach the yeah, I guess the final slide. So we have provided, I think, overwhelming evidence that this 42 indices exhibit modular properties. Where does it come mathematically? Perhaps one can generalize this Notor-Lefschetz theory to the case of one parameter models, even if they do not have a K3 fibration. More importantly, can we compute this non-vertical D4 D2 invariants? Then we will see hints of modularity. And I think this is probably the last thing I wanted to say. Let me just get back here. Yeah, and another natural class that we might like to look at are two-parameter models with torus vibrations rather than K3 vibrations. We can try to develop a similar story there. Okay, so sorry for going over time, and thanks for your attention.
Any questions?
Yeah, can you explain that still cannot completely solve the problem between invariants and now go to some of the high genus?
Why is there a bound on the on the Gromov-Witten invariants which are reachable by the direct integration? Well, I think you know this better than I do, but let me just say that every step in this integration process, you have to put boundary conditions to get the finite dimensional space of solutions. And we understand boundary conditions coming from the conifold point, coming from large volume, and we also use this Castelnuovo bound, which was previously conjectural, is now a theorem. That takes you only so far. But by the additional data that we get, we not only get Castelnuovo bound, we also get some explicit results for G invariants close to Castelnuovo. That gives us the extra mileage to push the genus to higher. But then why can't we go infinity? Well, it's this recursive prescription that I gave is explicit, but you have to have enough data on both sides, and it's very subtle play off against what you know about GV and what you know about GT. So there's no deep reason, but you can predict that it will break down at that point.
Due to time constraint, that's here. That's 7 hours again.